general relativity step by step. Now, we've got two different transformation laws here that are very different in spirit and very different in feel, and I want to give you an example of how these things work. So what I'm going to do is talk about Cartesian coordinates here, and I'm going to talk about the same physical system in h theta results, h theta space here. So here's my h theta space, and this is my x and y space. So that's my point P. Now how do these things relate to each other? X equals something and y equals something. X of course is h and y is h tan theta. H equals x and theta equals arc tan y over x. So they're in a nice simple relationship with one another here. Okay, so let me talk first about a covariant vector, and what I'm going to talk about is the gradient of a scalar, and that scalar is just going to be f, which equals f of x comma y equals k times y. So maybe that's temperature or something. So if I draw my x and y coordinates here, if I switch to red, these are contour lines of f of x comma y. Blah blah blah. So here I guess it's 0, that's k, 2k, 3k, and so on. So where does the gradient go? The gradient is just k in that direction, I guess. So we can, the gradient's uniform. It's the same everywhere. If this was heat and everything was the same conductivity, there'd be the same heat flux going upwards everywhere on this kind of bit of metal. So let's work out what the components of the gradient are. I'm going to call G, I'll switch back to black. I'm going to call G equal Gx comma Gy, and that's going to equal 0k, I guess. So Gx equals 0 and Gy equals k. So 1 and 2, 0 and k. So coordinate x is called x1 and y is called x2. Sometimes I use the numbers, sometimes I'm going to use the symbols. Okay, so what do? We're going to transform these things according to the covariant system. So what I'm going to do is, I'm going to draw it for a start. Here we are, and we've got lines of equal f, so that's k, 2k, 3k, that goes up there like that. So what does that mean? Let's go back to black. There's just a random point, that's theta and that's h. So we want, what do we want? We want di f by di h, di f by di theta. Okay, so that's the gradient in h theta space. So let's figure out what that is. That's di f by di h equals di f di x di h plus di f di y di h equals what? Di f di x is just 0, because when I say f here, f equals f of x comma y, so what that means is that for any point on this plane here I can associate a temperature with it, and I can do the same here, but of course it's a function of h and theta now, and h and theta depend upon x and y, so that's why I need to decompose this. Plus di f di y is just k, of course, times di y di h. Let's just have a look at that. Di y di h. Di y di h is just tan theta. From this formula here. I'm working out di y di h, and of course differentiating with respect to h gives me tan theta. Got myself a bit tangled up there. Okay, equals k tan theta. There it is. 0 plus k tan theta. And what's di f di theta? Well, that's equal to di f di x di theta plus di f di y di theta, which equals 0, because di f di x is 0, plus di f di y, which is k, times di y di theta. Di y di theta is just h sec squared theta. Okay, so the gradient, which is di f di h di f di theta, or I could write that as g for a gradient 1 and g2, where g1 is equal by definition to di by di h, and g2 by definition is di f di theta. Okay, actually this is going to be in the barred coordinate system. Equals what? Well, g1 bar equals from here k tan theta, and g2 bar equals kh sec squared theta, which I could rewrite in other terms. So what that's telling me is that we've got two components, two non-zero components, whereas in the Cartesian system, one of the components was 0 because these lines were horizontal, and so when you changed x, you didn't change your temperature, but when you changed y, you did. Here, it's somewhat different, because if you change theta by a little bit, you're not allowed to change h. H must stay the same, so you've gone up there. So if you change theta by a little bit, you've moved up in this direction here. And of course, if you change h a little bit, well, if you change h a little bit, you've got to move along this line here, because you're not allowed to change theta, and so you've moved up a little bit here. So that's why these components are like that. So let's just have a look at see how that works out in terms of just the tensor covariant transformation law. Well, it's just the same thing really, because all I've done is transform the basis vectors. It's just I put an f instead of a p there, so it's the same thing. So gi bar equals sigma over j, which I'm going to put in brackets because I'm going to try and wean myself off that. I don't need that. G j, that's got to go downstairs because I'm mapping a subscript to another subscript. And then it's this dx business by dx. Now what's happening? We're summing over j. That's downstairs, so that's got to be upstairs. That's unbarred, so this has got to be unbarred. That subscript I is associated with the bar, so that's got to be bar, and that's got to be an I. And then once I've written that out, I can get rid of this. Oops. I can get rid of that. Equals gj. What components? What was gj? That was 0 and k, wasn't it? So g1 bar equals g1 dx1 dx bar 1 plus g2 dx2 dx bar 1. So it should come out to be the same. Well, what are we trying to get here? We're trying to get k tan theta, aren't we? Okay, so what happens here? x1 and x2 are the same as x and y. That's just different notation. H and theta is x bar 1, and that's x bar 2. Sometimes it's easier to write the h and theta, sometimes it's easier to write the 1 and the 2. G1 was the gradient in the unbarred system, which was this one, which is just 0, plus G2, which was k, times dx2. What was x2? Was y, so that's di y by di x bar 1 was h. Di y di h was, from this formula here, just tan theta. It's the same thing, k tan theta. So it matches up here. So I can do it the way directly by doing vector calculus or multivariate calculus, or I can use the conservation law directly. So that's how that transforms. So let me just write that out again. Oops. something wrong with my pen. Cartesian. We've got a gradient which is equal to 0 and k, and in h theta space the gradient was, here it is, k tan theta kh sec squared, k tan theta kh sec squared theta, which I could rewrite in terms of x and y if I wanted. So that's what the system looks like. Okay, I'm going to stop there, and I'm going to do that was a covariant one, I'm going to do a contravariant one next. Stop there.